Hello friends. Today I'm going to give some insight into 5G technology. Um, Basically, we are going to learn what is 5G, what kind of services that we are offering in 5G, what are the different architectures possible in 5G networks. Then we see some internal details like 5G frame structure and numerology. Then after that, we will move to ENDC. What is ENDC? How it will be used in 5G? And what kind of barriers that we have in 5G? Then we proceed with 5G cell search, and then a practical session on how UE detects the 5G service when it is powered in a 5G network area, and what kind of barriers it will establish. And we will see some log messages to get some message level details. So before going into the technical details of this presentation, I would like to say that whatever information I'm providing in the presentation is not completely prepared by me. I have taken the references from various useful websites like ShareTechNote and various company websites like Keysight, Qualcomm, etc. And consolidated and presenting it in the presentation. Okay, let's get into the session now. Why we need 5G at all? We have already having a 4G technology live, and many of us are using it. Then what is the need for 5G? Basically, the need is driven by various kind of services that are going to be offered in the coming days. So basically 5G, ITU classified the 5G mobile network services into three major categories. One is enhanced mobile broadband. Enhanced mobile broadband is nothing but it's a broadband service, just like our landline, fixed line broadband service, currently whatever we are using in our home or in office, to provide the internet services to a group of employees or maybe a group of users using a cellular technology. So basically the aim is to replace the fixed line broadband services with enhanced mobile broadband, which is based on the 5G technology. So obviously this makes the life more simpler. We will get rid of unnecessary wiring and complications that are arising out of wire lines. Second major service category in 5G is ultra reliable and low latency communications. These ultra reliable and low latency communication services are basically services which requires highly reliable wireless connection between the communicating devices and highly and the connection should be having very low latency. That means the packet that the device sends to the other device should reach within a certain period of time, which is defined for this 5G technology. So basically these services comprises of all mission critical services where reliability and time is the major constraint. For example, remote surgery, autonomous vehicles, and surveillance equipment, etc. All these services where more time and reliability is more critical. And the third major category is massive machine type communications. Here, basically these services, all industrial IoT come into this category, where thousands of devices will be communicating with each other, uh, and at the same time, they may not be having huge data to become sent or received, but the volume of the devices that have to be camped on the network will be very high in that particular region or particular cell. So all IoT services which rely on 5G technology will come under this category. So we call these three categories of services as the cornerstones for 5G networks. These services actually uh, actually created the need for 5G technology to be evolved. So as we know, any technology is having a predefined KPIs, key performance indicators. Key performance indicators are uh, some metrics defined uh, with identified parameters, which the 5G technology has to meet, right? This table have collected few KPIs which are related to the 5G. These KPIs you can see even in 3GPP 38913 specification as well. So what are these KPIs? Let's see. Peak data rate. This is the maximum theoretical data when if you eliminate any errors and if you are using all the resources that are available. The target is for downlink 20 Gbps and for uplink it is 10 Gbps. Peak spectral efficiency. The spectral efficiency is measured based on bits per second per hertz. How many bits per second per hertz we are able to send or receive. So in the downlink, the target is 30 bps per hertz, and in the uplink, it is 15 bps per hertz. Control plane latency. Control plane latency is the time taken for a signaling message to reach from, say, the UE to the G node B. The control plane latency is defined as 10 milliseconds. User plane latency is the time taken for an application packet to transmit from UE to the G node B. Depending on the service, the user plane latency KPI target will differ. For ultra reliable and low latency services, 0.5 milliseconds in both uplink and downlink directions. For eMBB services, it is 4 milliseconds. Latency for MMTC, like massive machine type communication. For these kind of services, because usually these kind of services, the devices will have very less data to be sent, and not very frequently they send this data. For example, if you take your electrical meters, if they are made IoT based electrical meters, then typically an electrical meter of your home will send its reading to the centralized server maybe once in a month. And also it may not receive huge data from the server also. So for those kind of scenarios, so the delay time, the latency is not more than 10 seconds for sending 20 bytes of data in the uplink direction. Anyway, for these kind of communications, the downlink data will be very less, maybe few commands that the server might give. because all the computation and data storage will happen in the centralized server. So all the IoT end devices will be very lightweight. So, and the next KPI is mobility interruption time. So that is the break time when the device is moving. So for example, handing over from one cell to another cell, say. So the target is 0 milliseconds. That means 5G is intolerant to any break in the connectivity during the mobility. And the mobility speeds, 5G supports up to a speed of 500 kilometers per hour. So that means the device which is moving at 500 kilometers per hour still should be able to get its defined QoS when it is camped in the 5G network. And the last and final KPI is UE battery life. These are mainly for IoT devices. As I quoted earlier, for electrical meters or any such kind of IoT devices. When the device has to send 200 bytes per day of data and 20 bytes per day in the downlink direction. When 5 watt hours of energy is stored in the battery, then the battery is supposed to provide the energy for 10 years. Because obviously for IoT devices, users will not expect to recharge their devices so frequently, just like your mobile device, right? IoT devices will be huge. For example, if you have IoT based house, then all appliances in your house will be connected to the 5G network, and you don't expect them to charge on daily basis. If you put a battery, then it should come for years. And coming to the technical parts of the KPI, mainly these are some technical details of 5G technology. What kind of access scheme we are using? We are using CPU FDM, the downlink and uplink CPU FDM, DFT so FDM. Carrier aggregation up to 16 carriers we can aggregate. In LTE, I think only 5 carrier components we can aggregate. Bandwidth per carrier component, it can range from 5 megahertz to 100 megahertz for the FR1 frequency range 1, that is sub 6 gigahertz. And for FR2 frequency bands, it is 50 megahertz to 400 megahertz. And in 5G, subcarrier spacing is not fixed. There are multiple options for subcarrier spacing, like 15 kilohertz, 30 kilohertz, 60 kilohertz for 6 gigahertz. And for millimeter waves, that is FR2, it is 60, 120, and 240 kilohertz. We remember in LTE, the subcarrier spacing supported is 15 kilohertz. Of course, there is 7.5 kilohertz also, but that is only for eMBB services. So max number of subcarriers that are possible, 3,300. Modulation schemes that we use in 5G, more or less the same. QPSK, 16 COM, 64 COM, 256 COM. And it supports pi by 2 BBSK also. The radio frame length, it is same as in LTE, it is 10 milliseconds. And subframe duration is also the same, it is 1 millisecond. In LTE also it is 1 millisecond. And the duplex modes that we support, just like in LTE, we support TDD and FDD. But the difference is in FR2 range, that is for millimeter waves, only TDD is supported. For sub 6 gigahertz, TDD and FDD both are supported. Now the question is how we are going to achieve these target KPIs. Obviously, if you need some improvements in the KPIs, then there must be some changes in the architecture, in the design, in the technology that we are using at all levels. So in 5G also it is the same. So in order to achieve the target KPIs and provide the services that we have studied, basically 5G uses other parallel technologies like NFV and SDN. I think you would have some idea on NFV and SDN, network function virtualization and software-defined networks, which have been widely used already in scenarios where cloud-based services are provided. So in 5G also relies on these NFV and SDN technologies in its network deployments. The main concepts that are introduced in 5G are control and user plane separation. Actually, this is not completely new. Few already some 4G uh, core network components that are available in the market are already using this kind of control and user plane separation architecture. What is this control and user plane separation? Why we need this? So if you see, if you remember the legacy 4G network architecture, we will see we have mainly MME, S gateway and P gateway in the LTE core, right? So this MME, S gateway and P gateway, all the three components, all the three entities, they have both control and user planes together, co-located. For example, if you want to create a session, S gateway and P gateway and MME all are involved at the time of signaling for the session creation. And later on, S gateway and P gateway are involved in transferring the user data from the UE to the data network. So it's a kind of co-located control and user planes. In case of 5G, these control and user planes are separated out and they are maintained as separate entities. For example, P gateway is divided into two parts, P gateway user plane and P gateway control plane. They are two separate entities. Similarly, as gateway user plane and as gateway control plane, two separate entities. And MME is now freed from session management related function. So MME will no more support session management related signaling, session creation procedure. There is a new entity called SMF, which is introduced in 5G, which will take care of session creation. And MME's name has been changed. Now it is called AMF. So why we need control and user plane? What is the advantage that we are going to have by separating control and user planes? The main advantage is independent scalability of the control and user planes. For example, you want to update control plane part of your S gateway or P gateway, then you need not bring down the entire node. Now, because they are separated, you can update only P gateway control plane entity only. And still P gateway user plane will run as it is while this update is going on. And vice versa. If you want to update the user plane, you need not disrupt the P gateway control plane availability. So the main advantage is independent scalability. And another thing is if you are introducing any specialized applications, then you can independently have that proprietary services by having this CUPS architecture. Another thing is you can offload the traffic. For example, in few services, you may not, number of active users will be very high, and the data or the communication or the frequency of communication those devices are performing on a daily basis will be very less. In such scenarios, you will have more signaling load than user plane load. So in such scenarios, what you can do is you can have multiple control plane entities, and yet you can use the same user plane entity for all those control plane which belong to the same, for all the devices which belong to multiple control plane entities. That means you can offload the traffic based on the need, based on the user traffic, based on the uh, number of devices that are currently active, etc. And one more possibility is you can combine user plane entities into one entity, like you can combine P gateway user plane and S gateway user plane, make them co-located in a single entity. And you can combine S gateway control plane and P gateway control plane and co-located in a single entity. It depends. It depends on how you are planning your network based on various factors like the traffic load, the active subscribers, etc. So the second important concept in 5G networks is network slicing. What is network slicing? Network slicing is nothing but, yes, in the same network, you will divide the network entities into multiple categories, multiple subnetworks. And each subnetwork is specific to one particular service and one kind of subscriber set. For example, if you take the 5G services, eMBB service, URLLC service, and IoT service. As we learn, these services have different kind of KPIs. They support different amounts of active users. They support different amounts of data that the devices will send and receive. And they have their different computation targets, right? They have their timelines and all. So if one network wants to support all these kind of services, that means the network is having subscriber base, which is scattered across these three different kinds of services. Then obviously the network cannot have the same physical infrastructure to provide the required QoS per service type. So in order to provide the required QoS for the particular service a particular subscriber is currently using, there is a need for network slicing. So eMBB services basically requires huge amounts of, basically involves huge amounts of uplink and downlink data, right? Just like our home broadband services. So for them, the need of hardware and software will be different than URLLC services, where latency and reliability is more. So there has to be more high-end computation machines in the network. And for IoT devices, the need is the traffic might be less, but it has to support more active user base at any particular point of time. Millions of users it has to support. 5G, for IoT, the target is 10 million active subscribers per square kilometer, right? So with that kind of varied requirements, the physical infrastructure also needs to be varying in terms of capability, computation capability, storage capability, availability, etc. So 5G networks usually will have multiple slices, and each slice is pertaining to one kind of service. So, so then, take a typical scenario. We have a 5G network where it has all the different subscribers which belong to different categories of the services. Then how the network slicing will happen? So there has to be some mechanism in the RAN to decide when a particular subscriber wants a session, or he wanted to send or receive any data. Then that particular G node B or the RAN entity should be able to identify in which slice the subscriber information has to be routed, or which slice it has to use to provide the required service to this particular subscriber. So in order to find out the correct slice for a particular subscriber, there is a mechanism called network slice selection. It is a new function that is introduced in 5G, which is called NSSF, network slice selection function, which is basically to identify the slice for a particular subscriber. So if you see in the below diagram, so the G node B is communicating with the NSSF, and thereby it will derive what is the slice to be used for a particular subscriber. Now let's see a few differences between LTE and 5G core. In LTE, we remember there are a lot of protocols like diameter, GTPC, GTPU, DNS query, etc. So these many protocols will make the development and development process a bit complicated. You need a specific set of engineers who are having these protocols known. They should be aware of respect to the specifications, and they should be aware of these protocols. So as a result, you need to have different skilled people to do the R&D and do the development activity. So the 5G is mainly targeting to reduce these varied number of protocols and try to make a common technology protocol as a standard, so that these kind of development expenses, or maybe challenges that we are going to face in the development phase during previous years, they will be reduced with this new approach. So 5G basically supports HTTP2 based protocol with JSON APIs. So for whatever APIs that are being used in legacy technologies for doing development phases, they're all closed APIs. That means every operator will use their proprietary APIs to interact between different entities with the core network, not towards the RAN. I'm talking about the interfaces towards the core network entities, using which all the core network entities in any legacy network communicate. Even in 5G also, the interfaces the interfaces between the RAN and the 5G core remains reference-based, interface-based architecture only. But the other end, the all core network entities which communicate with each other. They can be a reference-based architecture or point-to-point protocol-based architecture, or a common open API-based architecture. And also we have DNS querying and all in legacy networks, where the network entities will, based on a DNS name, they will query the IP address and then use the IP address during session creation or maybe during data transfer. But the DNS querying has been completely replaced in 5G. They have introduced new concepts called network repository and a new function called network repository function, which will basically provide the same service as the DNS query, DNS servers. And in LTE network, MME and P gateway and S gateway all have the session management functionality. But in 5G core, session management has been completely separated out. There is a new function introduced in core network, 5G core, it is SMF, which will mainly for session management related functionality. And MME has been renamed as AMF in 5G. And obviously, as I explained earlier, P gateway and S gateway are now divided into P gateway U, S gateway U, P gateway C, and S gateway C. So basically, there are two different core network architectures proposed in 3GPP specifications. One is point-to-point reference architecture. User interface specific protocols will be used like diameter, GTPC, GTPU, etc. Another one is service-based architecture. It is in this kind of architecture, the network entities are managed in terms of the functionality they are providing. So network entities are, each network entity is having a well-defined functionality, and which is not like in LTE. So if you see the below diagram, so we have AMF, access and management mobility functionality. This is basically whatever MME does in LTE network. And session management functionality, SMF. This is what session management related activity performed by MME, S gateway, and P gateway together. So SMF is only meant to handle session management related functionality. It's a new entity. Third is policy control function, which just like PCRF and SCRF in legacy LTE networks. UDM, Unified Data Function, it is similar to our HSS in earlier legacy technologies. And AUSF, authentication server function. This is what AUF in legacy network. In legacy network, this functionality in some scenarios is part of HSS itself. There may not be a separate entity to provide the authentication vectors for the HSS. So here it's a separate entity defined, which is called AUSF. And UPF is the user plane function, which is mainly for handling user plane related functionality. That is, when the data transfer started, then this UPF functionality will come into the picture. So in the left side diagram, this architecture is mainly interface based architecture. So here we are, all these interfaces will use the same protocols like diameter, GTPC, GTPU. Some new protocols have been introduced. The right side diagram is the service based architecture. if you observe this architecture, the interfaces between, that means the air interface and the interface between RAN and the core network are still uh, stick to the same world method like interface based architecture. So hence we use the same set of protocols. But the interfaces towards within the core network, that means uh, the interfaces using which different entities of the core network will communicate are now based on the common API, like open API based technology, HTTP2 and JSON based APIs. So this is a major change. Whatever we are talking service-based architecture with HTTP2 and JSON will come into the picture in this particular area, not here. Here it is the same old protocols with some upgradations. But this area now becomes an open API, which will provide a lot of advantages, which is having a lot of advantages that we will see in the coming slides. As I said earlier, in 5G, the DNS will be abandoned completely and replaced with a network repository function. NRF is a repository where all 5G network functions register themselves when they are up and live. So whatever functional nodes that are available in the 5G core, they will be registering themselves with their IP addresses and service details in the NRF. So obviously any other node which wants to know about other nodes functionality or details, then it can query this NRF and then start communicating with the target function. And also this kind of architecture will facilitate functional nodes of different networks, say for example, HP element and VP element. So the VP element NRF can communicate with HP element NRF and know about a particular functional node in a P element. So this is possible because now if the operators are using this suggested open API based architecture in their core network. So this will help the operators to seamlessly make their network functions to communicate with each other, thereby reduce the human intervention and day-to-day activities in the backend office. For example, one subscriber of HPLMN moved to a different location and he's trying to camp on a VPLMN and he's getting registration failures. Now in a current scenario, what happens is the subscriber will contact the HPLMN call support and say that he is not able to camp in a roaming network where he is supposed to camp as per their subscription agreement. So typical scenario in the backend, they will contact the VPLM and backend office and try to resolve the issue, try to understand what is the error it happened, and all these things they will do manually and then find out. But if we have this open API based implementations, then what happens is this VPLM function, which is responsible for handling these kind of services, can directly communicate with the HPLM and respective function, retrieve the data, and then generate the reports periodically or take some corrective measures by informing the respective teams there and then. So these kind of advantages are there with service-based architecture with OpenAPI. Now coming to the 5G network architecture options. The 5G network, the 5G network architecture, there are two major categories. One is non-standalone architecture, and the other one is standalone architecture. Non-standalone architecture means uh, here the 5G network is not the primary network. It is the LTE network which is the primary network, and we will have 5G as a secondary network. Because this kind of architecture is the only possibility when operators are migrating from 4G to 5G and they start deploying their 5G network as, uh, as in small coverage areas in their 4G LTE coverage area. So then operators who are already having a wide 4G network deployed, then obviously they will prefer this non-standalone architecture to introduce the 5G services or to introduce the 5G network to their subscribers in the same operating area. Standalone architecture is basically for those operators which are deploying their 5G network as a whole. They don't have any legacy networks already existing. For example, Reliance Jio started their 4G services directly. They don't have 2G or 3G legacy networks before they start their 4G services, right? So straight away they deployed their 4G networks. Similarly, any operator, if they want to deploy a 5G network, then they will use the standalone architecture. But in general, all existing operators will use a non-standalone architecture to roll out their 5G services in phases. Because rolling out all 5G services in at once is not so useful, because in order to use those services, there has to be subscribers, there has to be devices, there has to be the industries which are ready to use those services, right? The whole ecosystem has to be evolved. So simply deploying a 5G network with all services will not generate any revenue for the operators. So in case of NSA, the anchor network will be 4G core and the secondary network will be 5G. In case of standalone, it's a 5G core, uh, uh, completely based on 5G architecture. These two options, again, there are some subcategories in, like where the aggregation of the data that will happen. For example, if one subscriber is downloading some data and the subscriber is now having both 4G and 5G capable devices and he subscribed for both 4G and 5G services, then in that case, what happens is when he is downloading the data, if the download data requires 5G QoS, then the EPC core, the data can be separated out in the RAN entity, or it can be separated out in the core entity itself. So 4G data will go through 4G to E node B to the UE, and 5G data will go to 4G core to G node B, which is 5G, and G node B to the UE. That is one option. If the aggregation and separation is at the core network. Otherwise, it will come to the E node B, and E node B will hand over the 5G packets to G node B using X interface, and then G node B will send it to the UE. So this is aggregation and separation at the RAN level. we will see in detail. So all these kind of possibilities will give you some almost 12 various different architectural options. So we will see the NSA non-standalone deployment options. The non-standalone deployment option basically 3.3a, 4.4a, 7.7a, 8.8a, and standalone options are 1, 2, 5, 6. Actually, which option to choose will depend on the operator's requirement. Is he migrating from a legacy 4G network and started deploying 5G as hotspots within the 4G coverage area? Then he will go for NSA-based options. And also in NSA-based options, we have multiple variations, right? So again, in that he will decide based on whether his 4G core is upgraded or his G node B is ready or not, depending on various factors. As I said earlier, the SA options are mainly for the operators which are deploying their 5G network directly. They don't rely on the 4G legacy networks. So let's see the non-standalone options. Here I'm describing 3, 3, 8, and 8A. So if you see the first option 3, non-standalone LTE assisted EPC connect. See the diagram here. Next generation core, that is 5G core, is not at all active here. It is not live. It is not present. The same old EPC core network we will be using, and the LTE E node B will be present, and the NR G node B will present. And EPC core will communicate with the E node B, LTE E node B only. And LTE E node B will have an interface with NR G node B using a X interface. And UE will have two RRC connections, one with the E node B and another with the G node B. And all control related information will be transferred over the LTE RRC connection. It will go to LTE RRC connection to E node B and E node B to the EPC. And if it comes to the data, then data will be transferred either through LTE E node B RRC connection or G node B RRC connection, or maybe on both, depending on the need. We will see this when it needs to transfer the data on both, when it needs to transfer the data on LTE only connection, and when it needs to transfer the data on 5G connection. That we will see later. But in this kind of architecture, you need to know there is no 5G core at all. We have old EPC. We have an upgraded E node B, which is now able to communicate with the G node B, which is now able to add a G node B to the UE whenever it is needed, more data throughput for attaining the 5G QoS. And the UE will have dual connectivity, one with the LTE node B and another with the 5G NR G node B. This we will call it as ENDC, Evolved Packet Core and New Radio Dual Connectivity. So you will have two RRC connections simultaneously. In the second option, there is no 5G core, only same EPC core, but this is an upgraded EPC core because it has to communicate with the G node B. And that means it will establish EPS bearers with G node B and EPS bearer with E node B also. And there is no communication between E node B and the G node B here. That means here the separation of data happens at the EPC itself. That's why we need to have upgraded EPC which supports 5G protocols. Okay, and it has to allocate the EPS bearers for the G node B also, and then route the 5G packets over G node B. So here in the first case, the aggregation is happening at the RAN level. And here the aggregation separation is happening at the EPC level. And option 8, here also there is no 5G core. EPC is the upgraded EPC, which is maintaining interface with the G node B. There is no interface with the E node B here. EPC for both data and control information, it will communicate through NR only, and the NR in turn will communicate with E node B. EPC will not communicate with E node B here. And as usual, UG will have two RRC connections. In the option 8A, here also there is no 5G core, same old EPC core with upgraded version. It has to communicate with NR G node B. Here EPC is having EPS bearers both with E node B and the G node B, but still the signaling part will happen over the G node B EPS bearers. Okay, here the aggregation and separation is happening at the EPC core level. Here the aggregation and separation is happening at the G node B level. Here, these are the options 7, 7A, 4 and 4A. Here we abandon the EPC. We will introduce the 5G core, which be able to communicate with the LTE node B and maintains EPS bearers with LTE node B for both signaling and data. And the LTE node B will have a interface with the G node B. Here 5G core will not have any interface with the G node B. It means it will not communicate directly with the G node B. All the communications will happen at the RAN level, that is at the E node B. As usual, UG will have two RRC connections, but the signaling happens only on the LTE side. And 7A option, here 5G core is present, EPC is not present. 5G core communicates with both the E node Bs, G node B and the E node B, and it will have EPS bearers with both, but the signaling still happens using LTE. In the option 4, 5G core is there, EPC is not there. 5G core will have EPS bearer only with the NR, G node B. It will not have any interface with the E node B. As usual, UE will have two RRC connections. All communication signaling part happens over 5G EPS bearers. And the final option 4A, here EPC is not present. 5G core will have interfaces both with E node B and the G node B, and UE will have two RRC connections, and UE will send signaling messages to the core network over 5G radio. And these are the standalone options. The standalone option, whatever you are seeing, the first one is the current deployment, where the LTE network is having EPC core, LTE node B, and the UE. If it comes to NR standalone, then it will be 5G core, 5G G node B, and the 5G device. For example, any IoT device, it need not be your UE handset, mobile handset. Any IoT device which is capable of 5G, then it can be having this kind of architecture. 5G, purely 5G device, communicating over G node B and connected to the 5G core. And in the 5 option, 5G core communicates with LTE node B, and LTE node B will have RRC connection with the device. And in the 6th option, we have EPC core communicating with G node B and communicating with the device. Here, these two options basically like interworking. 5G core can interwork with eNodeB, where you can utilize the existing eNodeB for providing the service. Now, coming to the 5G frequency spectrum. 5G frequency range is broadly divided into two parts, FR1 and FR2. Frequency range 1, FR1, is sub 6 gigahertz frequency range, and FR2 is a millimeter wave range. FR1 is basically from 450 megahertz to 6 gigahertz, and FR2 ranges from 24.2 megahertz to, 24.2 gigahertz to 53, approximately 53 gigahertz range. So FR1 has radio bands starting from N1 to N86, which are operational, which support TDD and FDD. And FR2 has radio bands starting from N52, N58, N60, and N61. They are operational only in the TDD mode. 5G supports flexibility in terms of subcarrier spacing. In case of LTE, we know we have only one subcarrier spacing, which is 15 kilohertz. But in 5G, we have the options 15, 30, 60, 120, and 240 kilohertz. Depending on the frequency range, the subcarrier spacing will be decided, because subcarrier spacing is related to the frequency that you are operating. So in both LTE and 5G, each resource block is spanning across 12 subcarriers, right? 12 even in 5G also 12 subcarriers per resource block. But in case of 5G, the slot durations vary depending on the subcarrier spacing chosen. So in case of LTE, only one slot duration we know, that is 0.5 milliseconds per slot. But in case of 5G, we have 1 millisecond, 0.5, 0.25 milliseconds, 0.125 milliseconds. So with subcarrier spacing increases, the slot duration decreases. In case of LTE, we know in 0.5 millisecond slot, we can accommodate 7 OFDM symbols if we are using a normal cyclic prefix, and 6 OFDM symbols if we are using the extended cyclic prefix. In case of 5G, we can have 14 OFDM symbols. Usually it is normal cyclic prefix only. So we can have a look at the various bands that have been defined in 5G specifications and the operating modes, whether they operate in duplex mode or non-duplex mode. Frequency ranges also you can see. So relook at the 5G LTE frame structure once. In LTE, one frame consists of 10 milliseconds. And one frame is divided into 10 subframes, each of 1 millisecond duration. And each subframe is divided into 2 slots. Each slot is of 0.5 milliseconds. And each slot can accommodate 7 or 6 OFDM symbols. So as I said earlier, this frame length is same in 5G. It is also 10 milliseconds. Subframe is 1 millisecond. But the time slot varies. Time slot reduces based on the carrier spacing. So in 5G, we use a new terminology called numerology to indicate the subcarrier spacing. So the numerology is denoted by the letter nu, and it has the values starting from 0 to 4. So total 5 numerologies are available. So 5 numerologies are pertaining to 5 subcarrier spacings, that is 15, 30, 60, 120, and 240 kilohertz subcarrier spacing. So the below diagram, you can easily understand the subcarrier spacing that is possible in 5G. So these are the slot durations. You can observe that the slot duration reduces if we are increasing the subcarrier spacing. Actually, the thing is, you will get a doubt why we need these kind of numerologies, why we need these kind of subcarrier spacings, 5 types of subcarrier spacings in 5G. The reason is in 5G operates at low frequencies, that is sub 6 gigahertz range, and millimeter wave range, very high frequencies, which are beyond 23 gigahertz range. So when we are operating at high frequencies, the signal is not tolerable for the fading. If you decrease the subcarrier spacing beyond certain limit, then it becomes more intolerable for fading and interference. So we need to strike a balance. We cannot have very low subcarrier spacings, and at the same time we cannot have very high subcarrier spacings. And that too, the recommended subcarrier spacings for sub 6 gigahertz is 15, 30, and 60. And for millimeter waves, it is 60, 120, and 240 kilohertz. So this is a pictorial representation how the frame structure look like depending on the numerology that we have chosen. So having these many types of numerologies, these many options for subcarrier spacing, we have some limitations. We have some applicability for each subcarrier spacing. For example, if you see the below table, we cannot use 60 kilohertz subcarrier spacing for synchronization signals. We cannot use 240 kilohertz subcarrier spacing for data transfer. It is only meant for synchronization and broadcast channels. So the nomenclature, the numerology has to be chosen and applied based on the channel that we are using. So the table gives you the complete details. You can have a look. And this subcarrier spacing is not fixed. So in any particular cell, the network can dynamically change the subcarrier spacing at any time, depending on the scenario or depending on the need. So hence, the subcarrier spacing needs to be communicated to the device and vice versa. So there has to be some communication for this subcarrier spacing to be used dynamically. So for that purpose, the device will communicate, the UG will communicate the supported subcarrier spacings and UG capability information. And also the network will communicate to the devices in various RRC messages dynamically. So coming to the synchronization part, we all know the synchronization functionality exists in any cellular technology. So any device which is powered on in the coverage area in any technology like legacy 2G, 3G, 4G, or 5G, first the device has to sync up with the network, and it has to be vice versa. Network also has to be in sync with the device. Then only the communication happens properly. So there are the synchronization involves two phases. One is uplink synchronization and the downlink synchronization. Uplink synchronization is the process in which UE figures out exactly when it has to transmit, where it has to transmit. which physical channel it has to use, and when it has to use. This is called uplink synchronization. This synchronization is achieved using a specific procedure called random access channel procedure, which is almost the same as in legacy network. And the second synchronization phase is downlink synchronization. In fact, the downlink synchronization happens first, and then uplink synchronization happens when the device is powered on in the coverage area. So the downlink synchronization is nothing but the UE detects the radio boundaries like frame boundary, subframe boundary, symbol starting, and all these things in order to read the system information and then accordingly configure itself based on the system information broadcasted by the network. So this downlink synchronization happens using synchronization signals. These synchronization signals are present in all legacy technologies, even in LTE also it is present. But there is some slight difference between LTE and the 4G. In LTE and the 5G. In 5G, we call synchronization signal block. But whereas in case of 4G, we'll say synchronization signals. Synchronization signals, basically we have two types of primary synchronization signal and secondary synchronization signal. Synchronization signals are nothing but a predefined sequence of data which has been placed in a particular word subframe in a particular spread across few OFDM symbols. So these are all predefined sequences so that any device which is compliant with the 5G technology would be able to detect these signals and then thereby read the physical broadcast channel information and then acquire the system information. So during the synchronization, any device will attain the radio frame boundary, subframe boundary, and they will be in time sync with the network, and they will come to know the physical cell ID where they are reading this information. So this is just an overall flow diagram. When the device is powered on, first the device will search for synchronization signals. Then after doing that, then it will read the PBCH, physical broadcast channel information like master information block, system information block 1, and thereby other system information blocks depending on the availability. So after that, after retaining the downlink synchronization, if the device is having any data, either it can be a signaling message or it can be application data, which needs to be sent to the network, then usually the device will initiate a random access channel procedure to attain the uplink synchronization. So after completing the uplink synchronization, the UG will have a dedicated connection with dedicated resources to send its data or receive the data. So the main difference between LTE synchronization and 5G synchronization with respect to the signals is, in case of LTE, the PSS and SSS and PBCH are not bundled together. If you see the first diagram, the first diagram here, PSS is transmitted in one time slot, SSS is transmitted in another time slot, and PBCH in another slot. In case of NR, PSS, SSS, and PBCH are bundled together. They will go as a single block. If you see here, each PSS, SSS, and PBCH is going together as a contiguous block of symbols. It will go, and in each millisecond, 10 millisecond frame, there can be multiple blocks of synchronization signals, that is multiple SSBs present in each 10 millisecond frame in case of 5G. And one more difference is in case of 5G, along with PBCH, we have PBCH DMRS reference signals. PBCH DMRS reference signals are reference signals basically for the UEs or the devices to measure the signal strength of the physical broadcast channel. There is a specific reason why they introduced these reference signals even when broadcast information is being transmitted. In case of LTE, we know there will be demodulating reference signals when we are using a MIMO technology. But in case of 5G, this DMRS is even present when we are sending the system information as well in the downlink direction. That I will explain you in the further slides. So if you see the FDD-based PBCH information and the spectrum resource element grid, if you see, the SSB consists of 240 contiguous subcarriers, and that means the SSB is transmitted over 20 resource blocks. We know each resource block spanning across 12 subcarriers. So 20 resource blocks means 240 subcarriers, starting from 0 to 239. And each SSB comprises of primary synchronization signal, secondary synchronization signal, PBCH, and PBCH demodulating reference signals. So in the right side diagram, if you see here, the SSB occupies 4 WaveDM symbols across 240 subcarriers, that means 20 resource blocks. And also you can see the synchronization signals are transmitted in the central 127 subcarriers, so that synchronization will not fail. I mean, it will be easy for the devices to, there won't be any interference or any fading. And PBCH can be in the extreme 48 subcarriers on both the sides. In the resource grid, if you see the black color rectangles, they are all demodulating reference signals, which are basically for the devices to measure the signal strength at the time of synchronization. So we will come to know why we need these DMRS instances in between the resource grid at the time of transmitting system information, at the time of synchronization. So in case of 5G, what happens is, because 5G is going to be operated at a varied range of frequencies, starting from sub 3 gigahertz to 55 gigahertz, very high frequencies like 55 gigahertz. So the property of a radio wave is that if the frequency increases, the range of the wave decreases. That means it cannot propagate in wider angles. It will propagate only in narrowed angles. So that's why if you see the leftmost diagrams, low frequency and mid frequency diagrams, if you see when it is single antenna, the waves, the radiation is propagating across throughout the coverage area in circular form. But if you come to the mid-range, then it becomes slightly lower, and you may need multiple antennas to cover the same coverage area. But when it comes to 5G, which is operational at very high frequencies like millimeter waves, then the coverage becomes very narrow. It almost becomes like a oval shape, and hence the coverage is available only for a group of UEs which are very present in very close proximity with each other and very close to the antenna. So then in that kind of scenarios, what we need to do to cover up all the area, all the devices in all possible angles, we need a concept called beam. So whatever you are seeing in oval shape, you can imagine it is a beam between the G0B and the UE. So this beam is basically a small coverage area covering few devices in few degrees of angle. So in order to cover the 360-degree angle, you need these kind of beams in all possible angles so that you will have full coverage in that particular cell. So hence in 5G, the beamforming concept is widely used, and in fact, it is not. It is you cannot avoid this because considering the frequencies that we are going to operate, uh, beamforming is the only option to provide the coverage and to utilize the spectrum to the maximum extent. Hence, when these many beams are forming, obviously we need techniques to beam management, beam shifting. When the device is moving from one place to another place, then obviously it has to be moved to one beam to another beam. So all these kind of algorithms are defined in 3GPP specifications. And these beam management, these kind of beams are required even when you're transmitting the system information, which is common for all the devices. So if you see here, when you're transmitting during synchronization itself, all the UEs, for example, in this diagram, if you see UE1 is in this place and UE2 is here. So because whatever signal that comes, it comes only in the form of a beam and has one scope for a small coverage area. The beams have to be swept from one angle to the other extreme angle so that it will cover the entire coverage area. So that means all the devices which are present around this circular area will be covered using the beam sweeping technique. That means if you see here, system information block 1, this is block 2, block 3, block 4. Okay. I'm taking in 10 millisecond frame, in 5 millisecond duration, there can be multiple SSBs that will be transmitted in multiple beams in multiple directions to provide the coverage for all the UEs which are trying to be in sync with the network. So this is called beam sweeping. So the same SSB will be transmitted in the form of beams in different directions so that it covers all the devices present in that particular coverage area. This is called beam sweeping. So in case of LTE, we don't have this beam sweeping during synchronization time. But here in 5G, it is required, especially when you are operating in millimeter wave range. Maybe if you are operating in sub 6 gigahertz or sub 3 gigahertz, it might not be required because you're almost operating in the same LTE frequency range that already implemented. So now the question comes, how the UE knows which beam is suitable to itself. For example, this UE1, which is now this UE1 can have access to these 3 beams. It can have access to multiple beams. It can recognize multiple beams, but these three multiple beams may not have the same signal strength. So by measuring the signal strength of each beam, the UE will pick up the most appropriate beam for its synchronization and then proceed further. In order to measure the signal strength of the beams, they have introduced this DMRS, demodulating reference signals, that we have discussed in the SSB blocks. So UEs or devices will measure these demodulating reference signals that are being transmitted along with the PBCH and then find out what is the best suitable beam for them at that moment. So if they move here and there, then the same beam will not be applicable to them, and it has to sync up to a different beam and then proceed. Because here the system information is a common information and many devices have to receive this information. So the device, it's the device responsibility to find out its own suitable most preferable beam and then sync up there and read the PBCH information and proceed further. But once the connection, once the synchronization is done and we have completed the ranch procedure, then when the UE is having a dedicated RRC connection, then there may not be a beam sweeping required for the UE. There, the beams will be mostly one-on-one. That means E0B will specifically form the beams for the UE depending on its location and the distance from the E0B. And if the UE moves from one place to another place while in connected mode, then E0B will put the UE in a different beam. So that kind of mechanism will happen. Beam shifting will happen dynamically. So there also the same concept, reference signal strength measurement is the concept that has been used in uplink and downlink to identify most suitable beams for communication. Even in MIMO in LTE, this in connected mode beamforming has already been used. So dynamically beams will be formed and informed to the UE or beams will be chosen based on the signal strength. So the same thing is applicable here, but here it is applicable even in at the time of transmitting the common information and synchronization also. So that's all in this session. In the next session, I would like to cover up initial access procedure, ranch procedure, basically, how it happens in 5G network. And then we will see some slides on how a 5G mobile will detect a 5G service when it is powered on in the 5G coverage area, how it will display its icon, what service currently it is providing, like 5G icon, 4G icon, etc. And we see some NAS level signaling messages and some signaling parameters which are being introduced for the 5G attach and 5G radio bearer establishments. In the same slides, we will come to know in detail about ENDC concepts, like having multiple RRC connections by the 5G device, 5G capable device, when it is in non-standalone mode. So all those details I will take up in the next sessions. Thank you. For any mistakes or any suggestions and improvements, please feedback in my channel. If you like the channel, please subscribe, share, and like. Thank you.